We're going to talk about we're going to talk about capacitor banks today. Yay. And this will be, other than the exam, which will be tomorrow, which is all regarding safety. This will be the last piece in the electrical power systems course that you're going to have to deal with as far as distribution equipment. So let me share a screen here, screen one. Some of this stuff through when we went through ELW 111 and ELW 112. So it's going to be a little bit of refreshing memories. Y'all see that?
Yep.
Okay. And then we're going to go into more detail of how to work on them, what their purpose is, and all that good business. Okay, so what do I have up on screen?
Capacitor bank.
All right, the distribution capacitor bank. There are transmission capacitor banks. Typically, those are always at substations. All right, so that is very, very elaborate right there. Transmission capacitor banks are based at substations. They serve the same purpose. Now, who can remember what's the purpose of a capacitor bank on a utility system?
It's the store energy to be released at a really quick rate.
Right, it's 60 hertz per second. It's really not a battery because it doesn't store for any length of time. It works on the 60 hertz frequency. But why do we put them on our system? What are they helping offset? This is a capacitive load. What kind of load do they help offset? Okay, so all right, with no answers there, let's go back and I'll go to a white screen here and we'll refresh ourselves.
Inductive loads?
Inductive, true. All right, they help offset inductive loads. And what are the certain types of inductive loads that we have out there on our system? Anybody remember what an inductive load is? An example of one?
The school.
The school is not a load.
Huh?
The school is not a load. The school is a place where we learn things. What's at the school? What's there a lot of?
AC units.
All right, and what's inside an AC unit?
Transformers.
What's inside an AC unit?
Oh,
What turns the fan? What turns the compressor?
Three-phase motors or
Motors, there you go. So motor load. Are y'all seeing this, by the way?
Yeah.
Motor load.
Hey, Shoemaker, can't capacitors, after you unhook them, can't they blow up after a period of time?
Everything can blow up after a period of time.
Like if they're just sitting there, like, can't they have electricity still in them?
Yeah, we'll get into that. That's why we're working on them today.
Okay.
So motor load is an inductive load. Actually, transformers themselves are an inductive load. Okay. Remember when we talked about our waveform, a resistive load that gives off light and heat was the most. Let me get this door closed. Yeah. I'm simulating today. How long was it okay?
Whenever you're available. I'm gonna be on this all day. Yeah.
Okay. All right, resistive loads, you know, like lights, stoves that have that element heater or whatnot. Those are the kinds of loads that we like on our system. Because when I'm producing voltage and then the amperage demand on the circuit, that's the characteristics of a resistive load. It's perfect. My voltage that I'm putting out, which is the top line, and the amperage that's needed to feed whatever I'm feeding, they're right in phase. Okay. Inductive loads are completely different. Okay, my voltage is here, and remember, this is a pure inductive load. No circuit's ever going to be like this exactly. All right, is what? Volts and then amps. It's 180 degrees out of phase. Right, not good. When I'm producing voltage at my generator, the amperage demand is completely opposite of that. So that's not what I want. So what do I put in my system to bring this more into phase? Capacitor banks, which are, let's get down here one more, if I can fit it in here, which are this. Okay, which are 180 degrees different from an inductive load. So that's why we use capacitor banks on our system. We want to bring it as close as possible, which it never is exact, to in phase. Oops, in phase. Okay. So that was a little refresher that we had back from ELW 112. Clear all drawings. Okay. So we introduce capacitor banks on our system for those inductive nodes. Now, where geographically do I need to put them? If I've got, let's see, Randall used the example, I've got the college, it's an inductive load. Should I go ahead and put it close to the substation because the college is on the circuit, or should I put it close to the college because that's where the inductive load is?
Close to the college.
Close to the college as possible, okay? And you'll remember by that picture I showed you on Google Maps, right out here on Highway 501, there's a capacitor bank right in front of the school. So that helps offset the inductive load that's in the college. Okay. All right. Yeah, is this stuff starting to set off some light bulbs in remembrance of what we did before?
Yeah, a little bit.
Okay. So if I were to ask the question, why are capacitor banks needed? What would be an answer, a good answer to that? To boost the voltage, to boost the amperage, to improve system outages, or to offset inductive loads? What would be a good answer out of those?
Offset inductive loads.
Offset inductive loads, exactly. Okay. All right. So each one of these capacitor bank itself, let me stop this share, start another share. Has a, you may know if you see that.
Got it.
Okay. So a capacitor in the bank itself, they have the capacitor cells in the bank, and you'll see the different sizes here. That looks like a 100, 200, 300, 400. And when I say 100 on the left-hand side, that rating is in kVARs, K-V-A-R-S, kVAR, small s. Kilovolt amp resistance. And really, you don't need to know as much information as the kVAR itself as you do the sizing. You as an installer are going to get a work request that says, I'm going to need to install a capacitor bank that has a total of 1200 kVAR. And remember from this picture that we had before, capacitor banks are installed on all three phases all the time. So I've got one switch, one switch, one switch that's attached to a phase. We'll talk about vacuum switching here in a moment. Then I've got two cells per phase. So that's one. You look at the cells that are in this unit. There's 1, 2, 3, 4, 5, 6 cells in this bank. Now, by the size of looking at these are pretty much more than likely 400 kVAR per cell. So if I was to ask the question, if these are 400 kVARs per cell, how many kVAR are they per phase?
8 kVAR per phase.
400.
Oh, 800 kVAR.
There you go, 800 per phase. If I was to say how many kVAR is the total bank, you would say
2400 K-bar.
2400. Well, yeah, you can take all 6 and multiply them by 4, or you can take each individual phase, and there's 3 phases. That's 800, 800, 1600, and another 800 is 2400. Okay. For your knowledge and what you're going to need out there in the world is, they don't show it on these right here. There is a nameplate on each one of these, and it's going to show in writing 100 kVAR plus all the other pertinent information, 200 kVAR, 300 kVAR, 400 kVAR. All right. I'm not going to go to a unit and put mismatched kVARs or units inside a bank. It would not be logical to put, let's see, this is 2400, 12 200s in here. Okay, you're gonna have to put 6 400s. Is that making sense? For one thing, the rack won't hold it. And 2 is you just have more potential for things messing up on you. If one messes up, then you got a problem. You have to take the entire thing out of service. Okay, so let me zoom in a little bit of this. So if I need 800 kVAR out of 2 400 units, electrically, what am I doing with the unit itself? Okay, the side that you see right here, this is the grounded side. The side that's closest to us, the bushings that are closest to us, is the grounded side, and all of the units are grounded on one side of the bushing. On the back side of this, you'll notice off the left-hand switch, I go into one capacitor and another. That is paralleling. I'm paralleling 2 capacitors. Each one is 400 for a total of 800. Is that understood? I guess not. If I have 300 300 kVAR banks, how would I need to wire them?
Two 300 K-bar banks, you would connect them in the back with the ground, and then connect the what'd you call the vacuum?
Yeah, the vacuum switch on the left. Right, sure. Okay, it's the same. If you think of this, it's the same thing as almost as 3-phase as far as bushing use. I've got a left-hand bushing and a right-hand bushing, or the bushing that's furthest away from me and the bushing that's closest to me. The bushing that's closest to me on this bank right here, all of them are grounded. So the same bushing on every cell is grounded for one phase, and that's the left-hand switch right there and the left-hand vacuum bottle. I've got 2 same bushings energized. All right, so I've got a 400 cell, that's paralleling. I now have an 800 kVAR capability right there. You have to parallel the cells in order to get 800 kVAR out of 2 400 kVAR units. All right. Okay, I'm going to stop that share. Let me know if I'm getting too quick on you guys now. So if you got questions, let me know.
So you just you're paralleling them by sets or couple, like every
Yeah. If I
got it.
And really that's got to do a lot with how much capacitance I need on the
each
location
phase.
in comparison to the inductance that's out there.
Yes, sir.
Okay. And like I said, they make different size units. Now, when you start getting up in the 1200, 2400 kVAR range, that's a pretty big amount of inductive load that's out there.
Yes, sir.
Are you guys seeing my white screen right here?
Yes.
Okay. So I'm going to look down on the capacitor unit. I got one bushing here and one bushing here. And we'll say we'll just say it again. It's a 400 kVAR unit. That's the rating for it. All right. If I go into this on the bushing here, and I ground this one, I'm only going to get 400 kVAR capability out of it for that phase. This is a phase. Paralleling is putting another unit in the rack, in the hold right there, right with it. Now I'm going to ground this one and go to ground and just take this lead and go over to the next unit. That is paralleling the unit. All right, 400 times 2, now I have an 800 kVAR unit. And do understand, that is for that phase. If I do it on that phase, I've got to do it for B and C also. Good? Okay. All right. So the question is going to be, can I parallel capacitor units to increase the kVAR? True or false? Yeah. All right. Okay, so let me stop that share. What time are we holding? It was 9:35. Well,
9:35.
9:35. All right, so we had those waveforms before. I'm gonna ask this question right here. Capacitor banks attempt to bring system blank in phase with amperage. Do you remember the waveform that I had right there? All right, let's go right here and we'll take a break after this one. All right, I had the waveform. Volts. And then I have, let's just throw it off a little bit. I got some inductive load. Amps right here. Amps is leading volts. The question is, capacitor banks attempt to bring the system what? Volts, amps, inductance, or resistance in phase. Remember, in phase is a just like this. Okay, so I've got V and A here. What's a capacitor bank try to do? Does it try to bring resistance in phase, inductance in phase, amps in phase, or volts in phase?
Inductive.
What?
I don't even see inductive on here. I only see volts and amps.
You asked what it was trying, what the thing was bringing into phase.
Right. The two things that are out of phase on this top diagram right here are volts and amps. I don't see an I for inductance. All right. Let's do a little discussion here then.
It's trying to
Is it
bring,
trying to bring amps?
Nope. Let's clear all. When we have an inductive load, like a motor load, correct?
Mhm.
Okay. What turns that load inductively? I'm inducing a magnetic field, correct?
yeah,
Right. I'm using volts, and to turn the motor, what is turning the motor?
amps.
Amps draw, right? That. Right. Remember, as soon as I go inductive, I go into a 180-degree opposite waveform than volts. Right. A capacitor bank is not inductive, it's electrostatic. Volts. Okay, so whenever I bring this online, I'm increasing and improving my waveform on the volts line. So back again. Volts, amps, out of phase. Capacitor banks attempt to bring the system what? In phase with the amperage.
Volts.
Volts, right. Electrostatic volts. That's what a capacitor bank does. You only have the one to choose from. There's no inductance here. on this line. There's no resistance on this line. This waveform. Okay, only volts. It attempts to bring volts and amps into phase. I want a more, and I'm going to clear this one off. Like I said, there's never in the world out there going to be a perfect waveform all the time. Motors turn off and on, capacitor banks turn off and on, but you want your system. I'm just draw it out just a little bit to be as close to in phase as possible. A, B, okay, and that's what capacitor bank does. Now, I'm just going to give this for a little example right here. The capacitor bank is offline, and the capacitor bank comes online. We'll talk about how SCADA does that a little bit. This volt line is going to move up and try to get right in phase with amps. If I put too much capacitance on the line, it'll actually put the volts line way out here. Okay, now my line has too much capacitance. But every time a capacitor bank operates, opens and closes, it is moving the volts line. That is it, and that is all. It is trying to bring the volts in phase with amps, right? That's the thing I can control on my system. Can I tell the customer to turn his motors on and off to help with my waveform? Hey man,
Yeah.
shut down 4 air conditioners at the college. You're disrupting our power system. Huh, that ain't gonna happen. But can I open and close the capacitor bank on my own system to help accommodate for a poor waveform?
Yeah.
Yeah, so that's why. And then that in that world, I can't make amps change. That's the customers doing it to me, but I can adjust my volts. And that's what a capacitor bank is there for. Okay, let's take a break. It's 9:41. Let's say 9:55. Break time.
Sure.
As far as the monitoring process, I mean, obviously, if I've got capacitor banks that are out there on my system, bring up a white screen here. Whiteboard, share. All right, clear this off. All right, so we're all familiar with SCADA. Just as a reminder here, what's the purpose of SCADA? Why do we use SCADA on our electrical system?
Supervisory control, acquisition.
And data analysis, correct.
data analysis.
Okay, so really, I mean, if we want to shorten that up, we monitor and control, okay, our circuits. All right. In the background, of course, there's a lot of automated operations that are going on. I only need to monitor and control. There's recording that goes on here. Okay, we can record a lot of data. Okay, but a lot of stuff is just done automatically. That's obvious by the substation circuit breaker. Do I need to station a man at every circuit breaker at a station in order for it to operate correctly? No. All right, it'd just be kind of dumb. In my dispatch center, right? I think when I left, there was right around 480 circuit breakers in the Grand Strand area. Do I have to have a guy that's sitting there all day long monitoring all those circuit breakers?
No.
No,
Well,
of course not. There's automation that's going on. Now, if there's an event, if there's a major event or something that happens in that time, I'm going to get an alarm. Okay. And then I'm going to go focus on that one that I'm having an event on, maybe 2 or 3 at the same time. But I'm not going to be monitoring all 480 at the same time. So SCADA is doing a lot of work in the background and of course, our equipment out there in the world. As far as capacitor banks are concerned, they are controlled by SCADA, but it's only a one-way operation, right? SCADA will open or close a bank as required, okay? It'll send a signal to a radio that's mounted on the pole where the capacitor bank is, and its purpose is to open and close capacitor banks. Okay. Now, how does it know when to do that? Where's the information coming from saying your waveform's out of shape? Okay. You're looking kind of bad here.
From a breaker?
You're close. All right, it's the voltage regulator. Okay. The voltage regulator has measurements and it is monitoring two things: volts and amps. Okay. Inside of it, and it's also watching what they call power factor, right? Power factor refers to my waveform in volts and amps. Right? Once it sees that the power factor is out of a certain level, amps and volts are not in phase by a certain level, it'll send a signal to the SCADA radio, and the SCADA radio will then send a signal to the capacitor bank. Open, all right? My power factor is too high, I need you to open. My power factor is too low, I need you to close. So it periodically sends that signal out depending on the power factor that's at the regulator at the substation. Does that make sense? Good idea?
Yeah.
Sure. Do you think that a capacitor bank, there are some locations that do this. During the daytime, all the air conditioning is running here at the college. It's full of students in the fall and spring. And do you think I'm going to need a little bit more capacitance during the daytime than I am at night?
Yes.
Yeah.
Sure. The voltage regulator at the station, which is monitoring this circuit all the time, yeah, the power factor is a little bit out. I'm going to go ahead and close. And it might be just, 8 o'clock in the morning, everybody's coming in. Okay. 6 o'clock at night that, everybody's left. The motors are not turning as much. Well, voltage regulator's monitoring that also. I'm going to open that bank because it does take power to operate the bank for it to be working in the first place. Two is, I'll do this waveform. That's my volts line.
Hey, sir, real quick.
And here's my amps line way back here. I don't want to make my volts line way too far ahead. If I got too much capacitance on the circuit, then I'm defeating myself. Okay.
Real quick, sir. By the way, he's trying to get back in. I guess he got kicked out.
Again, thank you very much. Let's see more. Participants. By the way, and Ross Miller. There you go. They're back in. Thank you very much. Okay. So the question will read, the blank monitors circuit power factor. What monitors the circuit power factor?
The SCADA.
No, SCADA controls it.
The voltage regulator.
All right.
Voltage regulator. There you go. The voltage regulator in conjunction with SCADA monitors circuit power factor. Okay.
Okay.
Good deal. All right. Let's talk about this a little bit. We did this before. You got to watch the wording on these questions when this question comes up. We've talked about waveforms a little bit this morning. Okay. Here's, let's come back here. I'm going to make this volts line. I'm going to make this amps line. Now listen to the wording of the question closely. When the voltage is leading in the electrical circuit, and when I mean that, by this example, this voltage is leading, it's ahead, it's in first place. An electrical circuit, the circuit is what? Capacitive, inductive, or resistive? Voltage is in the lead. Voltage
Voltage
refers
is in the
to-
lead in the capacitance.
Yes.
Okay.
It's
Voltage is in the lead.
capacitive, right? My
Yes, sir.
voltage is ahead, so
Mhm.
it's a capacitive circuit.
Yes, sir.
Very well done. Good. All right. Voltage is in the lead.
Mhm.
When the voltage, sorry about that, I hit the same question. When the voltage is lagging in the circuit. So let me draw that circuit up here. I'm still sharing that white screen, right?
I can answer that question.
You can, right? Go ahead.
It's inductance, right?
It's inductive, right? My
I was
amp
gonna
line
let
is
you-
ahead.
Yes,
Right.
sir.
My amp slide is in the lead. That means I have inductive load on the circuit. Fantastic. Good deal. All right, so let's talk about a capacitor bank. And I'll give you an example by maps here. Clear all drawings. Let's unshare this. I'm gonna go to Google Maps. I'm going to take you to Grand Strand Water and Sewer.
Mr. Shoemaker,
What?
and just to for clarification, the reason why you have inductance is because of magnetic pollution, right?
Well, you have inductive loads, which are motor loads.
Oh, yeah, that's right. The motor load. Yeah, that's right.
Correct. Okay, good deal. All right, so where am I? I am in Myrtle Beach. I'm going to the Ripken Fields. Let's go zoom down here. Need to get over to Helicopter Adventures, Grand Strand Water and Sewer. Fantastic. Let's go to satellite view. See how close we can zoom in on this. All right, so we're just gonna throw out a simple question here. Here's the substation,
Mhm.
21st Avenue substation. I'm gonna drag over here, zoom out a little bit. This is Grand Strand Water and Sewer. So of course, first question here, do you think there's a lot of motor load out here?
Oh, yeah.
A ton of it, a ton of it. All right.
Oh,
Do
yeah.
you think that motor load with all these pumps running all the time, do you think that motor load stays on all the time?
No.
Yeah.
Yeah, why not? I mean, I flush my toilet at night and daytime. Pretty much everybody does. Okay, so that's really what they call a constant motor load.
Okay, so it's constantly on. Okay.
Yeah, motors are running all the time. In fact, you can see a little bit of fun going on right there. Okay.
Got it.
All right. So what I'll have here, and this is close to the motor load. Let's see if I can zoom down to it. Get close as I can. I come out of the substation with a feeder, and it actually comes from the right-hand side up here. And let me see, I'll zoom as close as possible. That's as far as it'll go. Do you see that pole that's right there in the middle?
Yes, sir.
All right, that's a capacitor bank hung on it. All right, it's what we refer to as far as the capacitor bank controlling a fixed bank. Now, what do I mean by fixed bank?
Meaning it's constant.
It's constantly what?
It's constantly so
Constantly drawing the same load.
All right, so I'll give you a hint on this. There's no SCADA control. It's constantly
so-
what?
it's constantly regulating or
It's constantly open or closed.
Open. Or closed.
Closed. Remember, I've got a motor load that's going on 24/7 over here.
Yeah.
it's constantly closed
It's
because
constantly closed. That's what
Because
we call, right, that's what we call a fixed bank. No
Is it-
SCADA control, constantly closed.
since there's constant induction, that capacitive bank is counteracting that inductive activity that's going on.
Exactly, 100%. 100% correct. Fantastic. Guys are catching on and doing very well here. All right. Let's see. So let's talk how much, all right, during storage transport. All right, so let's go back to this picture. Here. So let me start this share screen. Screen one, share. So we referred to this picture a little while ago when we first started out. And I want to go through the process of how I get voltage from my primary. By the way, it's just all over the place, isn't it? Okay. All right, part of this, then there's a couple of different reasons why we use what they call a vacuum bottle on a capacitor bank. First, in a vacuum bottle, which you see on the right hand side is a transformer. So that gives me voltage here so I can operate switches. On the left-hand side, you'll see one of the vacuum bottles. There's one right beside it for the center phase. When I say vacuum bottle, what do you think the purpose of the vacuum bottle switch is? Why do I just use the regular cutout that's up there? Why do I also include a vacuum bottle?
Does it have to do anything with arc? I mean,
Load breaking the arc.
Excellent,
Yeah.
excellent, gentlemen. Yes, I'm
Yeah.
breaking and making load in a vacuum. Okay. Two, and the other part of this right here, you see the wires coming out of the bottom, they're controlled. So when SCADA sends a signal, this is the control part right here. This is the piece and component that opens and closes. Obviously, I can't have a guy standing here at the cutouts. Well, you need to open those switches. You need to close those switches. No, that's not going to work. So I could put controls in a vacuum bottle. All those cables right here that you see coming out of the bottom go down to the control panel and a radio. And these will automatically open and close when they receive a signal. So two main purposes. I can break and make loads inside of them. Two, they're automated. SCADA can control them. Okay.
Gotcha. Hey, Mr. Shoemaker, on
Hey,
that
what's up?
on that pole right there, I mean, they don't allow people to climb, right? It's usually mainly use the bucket truck, right, to fix anything up there, right?
Well, depending on your organization right here, let's talk about this, Professor V.
Yep.
Let me share the screen back. I would take it on a per case basis.
Yes, sir.
If I had a guy in a bucket truck that de-energized the bank, opened these switches and took these high side risers off and installed his rubber goods, I'd be okay with a person climbing up here and doing work.
Correct.
All right. Can he do it by himself just climbing? I seriously doubt it.
No, it's too bulky.
No. Okay. This framing style is not ours. That's obvious. Is not really good. It doesn't seem to be much distance. Let's zoom out here. I know where another capacitor bank location is. You're real close. This is actually on a 34 kV circuit. Drag my man over here. Bang, where am I? Oh, dude, see? Got real close. Okay. This one seems to have a lot more clearance in it. So I'd open my vacuum bottles, open my switches, take these risers off. Yeah, you've got 10 feet or more of clearance in this area to be able to work on it with your climbing tools. Yes.
Yeah. The first picture you showed of that cap bank, that'd be more or less along the lines of Duke's construction. And I mean, like you said, you could go up there, de-energize it, ground out the bank, and then the guy could climb the pole to assist the guy in the bucket, but it's hard to really change anything out of that rack.
Yeah,
On the pole.
I would agree. It's a climbing nightmare because you don't have much room to work here.
Mm-mm.
Yes, sir.
That's up to the company that's going to be telling you what to do.
Yeah.
Okay. We'll get into this in just a moment. You'll notice right here, this capacitor bank, right? Do you see any kind of controls on the pole?
No.
No.
Okay, there's a specific reason for this. This is a 34 kV capacitor bank. See if I remember which pole it's on. I think it's this one over here. Yeah.
Is that for the
The
water park?
controls, that little gray box, are way over here. We'll talk about this in just a moment. So SCADA is talking to the radio, and controls are in this panel right here, a good, I'd say 100 feet away from the capacitor bank. We'll get into that reason in just a moment.
Is that in case a car hits it?
No, no, it's for your safety. Okay, all right, so let's get back, let's unshare that. Now we're going to get into some meat and potatoes of how you guys work on one. You know what it's for. So how do you work on a distribution capacitor bank? Okay, let me get a whiteboard going on up here. It's kind of a lengthy procedure. You and crew that you're working with, as far as working on a capacitor bank, are going to need to know these steps to do your work. Okay, so number one. All right, in normal operation, day to day, will a capacitor bank open and close automatically, automated?
Yeah.
Yeah, we just discussed that. That's what it's meant to do, okay? So the first thing you're gonna have to do when you get ready to do any work on a capacitor bank is obtain a CWP, capacitor. Sorry about that. Work permit. Okay, what a capacitor work permit is, and you get this from the dispatchers. What this does, the capacitor work permit, the dispatchers are just going to tell the regulator at the station, or the controls at the station, right? No more communication. You obtain it, there's going to be no more communication between the capacitor bank and SCADA. Why do we want to do that?
So in case somebody messes up and re-energizes it, you're not up there?
Well, you say somebody, in case it does it automatically.
Oh, okay.
Yeah, you want to take the capacitor bank work automation away. You don't want to be working on it and it closes on its own or opens on its own, right? You don't want that to happen. So you want to cut off communications to that capacitor bank you're working on. And you can do that by pole number, or you can look in the control box and there's an address for the capacitor bank itself. Okay. 2, send open signal. Now the dispatchers, they've cut off automation, but they can still send open and close signals manually from the dispatch center. When they send an open signal, what are we opening? What's going to be opening on the capacitor bank?
The vacuum bottles?
Right, opens vacuum bottles. How do you spell vacuum? V-A-C-U-M-M. Sounds good. Bottles. All right. 3, confirm open. This is you. They can send the signal, but they can't see the difference at the bottle itself. And I wish I had a picture of it, but I will bring this one back up. Let me stop this share. Start you another share. Stop share. Share screen. Screen uno. Share. All right. Primary. They'll either have one or two things that you can confirm it open with. On the bottom, they'll have a window with a red flag or green flag, or they'll have a handle on the side that's either up or down. All right, the handle on the side up is closed. The handle on the side down is open. Green means what? Same as a substation breaker.
Open,
Open, red means
closed.
Oh,
closed. Okay. Most of them, a good, I'd say almost all of them, I haven't seen very few of them, have both. They'll have the flag at the bottom and the handle in case you need to manually open it yourself from the outside. But you still have to confirm. You see the two that are here on the left side. One is hidden by the bank itself. You have to confirm all three of those vacuum bottles are open.
And if the handle's up, it's open.
Closed.
Closed.
Handle down, open. Okay, so confirm open. Now let me write this. Where did I put my little, there it is. Confirm open by flag, a red or green, or by handle, or both, if it's equipped that way, okay? Now that load's been broken, if it needed to be, now that we confirmed all three vacuum switches are open, now we can open the cutouts. Okay, so now we have a circuit from that previous picture I just showed you before. All right, I'm going to add this in there, and this is for safety purposes. Remove high side risers. It just gives you more room. You don't have that jumper coming off the top of the switch going to the primary that's energized. So let's remove our high side risers. We have plenty of space to work in with no energized lines around it. 6, very important here. Wait 5 minutes. Now this is mandatory for us. If your company tells you to wait 10, wait 10. If it tells you to wait 15, wait 15. Now, Robbie, how long did you guys have to wait?
We just waited a couple minutes and then grounded it. So
Right. Wait 5 minutes. 7, ground. Now, why do I wait 5 minutes?
For the capacitors to bleed off.
Yeah, there's a residual charge. And you want to wait for that to bleed off in that 5 minute period. Some, like I said, some companies might specify a little bit higher. Wait whatever they specify. Ground the bank. Okay, that is it. You're now ready to, and I'll put the step down there, do repairs. It might be taking out a cell, it might be tightening some connections, it might be doing whatever you need to do. Replacing a vacuum bottle, whatever. Now you can do repairs on the bank. So that is how to take bank out of service. Vitally important is that 5 minute wait. See, a lot of guys will get to remove the high side risers, which that's going to take a little time, and they go to ground the bank right away. You might get a good arc if you do that, if you don't wait that amount of time. Okay. Good on that. What time are we holding? 10:33. Do you think? Oh, okay. I kind of left something out here, and I went against the grain of what I usually tell everybody on my steps. When I waited 5 minutes, what do I do before I ground anything?
Yes.
Test it.
oh
Tick
yeah.
trace. Yeah. How about that? I'm looking at my steps on another piece of paper. Tick trace, hot horn. Test it first. So we're going to go 6, 7, 8, 9. Okay, so tick trace it, then ground it. Good deal. All right. Well, it's 10:33, and I know I made you guys wait a little bit because I had a meeting with the boss man. Let's go for about 11 minutes here. Let's go to about 10:45. We've got about 4 different more things to go through as far as capacitor banks are concerned. Of course, we got to put it back in service. And I think we'll be close to ending the day, at least for us. You guys get to do a quiz on this. So we'll see you back at about 10:45. Resume recording. All right, so we took the capacitor bank out of service and we worked on it and did our repairs. Got everything done. What are the steps to put it back into service? So we're going to list those steps next. So 1, if we
Cancel
have any,
CWP.
excuse me,
I was just gonna say cancel the CWP.
almost, we're not there yet. Okay, we've got to do some work before that happens. Okay, so 1, if we have grounds installed, we're going to remove our grounds. Okay. 2, install
Oh, yeah, that's
our
perfect.
high side risers back. That's the wire that comes off the top of the switch. It goes to our primary. Okay. 3. Now remember, through this process, we've had an open vacuum switch the whole time. So this is okay to do. We're not actually energizing the bank yet because we have an open vacuum switch. Is close, fuses, all 3 phases. Okay, 4. All right, this is another vital one in this process. We're wanting to use the benefit of SCADA here. As far as, in Professor V, put your insight on this and any kind of experience you have. As far as the potential for a major fault or a serious explosion, capacitor banks fit the bill.
Yes.
Yeah, capacitor banks can be extremely volatile when they're
Ooh,
energized.
yeah. Heck yeah.
Okay, so we're going to use the benefit of SCADA here. Move to safe distance. Okay, obviously, we're going to follow that rule that we did in the safety thing yesterday. Don't stand under the fuse barrels. But I don't mind, getting 40, 50, maybe even more feet away.
Yeah.
So move to a safe distance.
Then, our procedure was just like you showed on your controls, it was across the street away from the bank. Our controls are always on the same pole, but there's a time delay from the time you close the switches in, when you put it back in the remote or re-energize the bank to close in those oil switches on it or vacuum switches. You had a 30-second delay to move down the line away from it.
Okay, well, that's a great procedure, and that's the way they did it there. We did not. As soon as, and we'll get to this point in our step process right here. As soon as we requested the signal to be sent, it was sent. So let me go to the college here, unshare this one. Stop share, come back to it. Share screen 1. And we're at the Coastal Carolina Discourse. Where are we at? Okay, here we go. Let's pull out the 501 and look at our capacitor bank here at the college. It is, wow. Got lucky, didn't I? Dropped this right on it.
You're not sharing it.
Oh, wow, why not?
I don't know.
Share screen 1, share. How about now?
Yep.
Oh yeah, there she is.
Fantastic. Okay, so here's the control box. Okay, and it's got, I don't know if you can see, it's got a little black antenna on it. So you can actually, that's where the radio works. And they put an external antenna on it. So it picks up the signal better, but it's on the same pole. So I've completed all my work up here. I've done everything I needed to do. The vacuum bottles are still open. The switches are closed. When I say move to a safe distance, I'm probably going to come, 30, 40, 50 feet away in any diameter around the pole. That's what I mean by safe distance. Okay, stay away from it. If I've got that option and the capability to close something by SCADA, use it to its benefits. Stop share there. Share screen, whiteboard, share. All right, then you're going to call your dispatch. And you're going to ask for what? Send,
Closing
close,
signal.
close signal. Okay. Now, once that closed signal is sent and you hear confirmation that it is sent, nothing's happened out there. 6, confirm vacuum bottles closed. How would I confirm that from looking at the bottom?
Red flag is closed,
Red flag,
or if the handle is down
up.
or up.
All right, handle up, or a combination of both. All right, there is, and Professor V, you get on this one too, as far as your dispatchers and the information. SCADA is still working,
Yeah.
right?
That's right.
You will confirm that in the field. Some of your dispatchers will come on, and it's kind of a nice added deal right there. They will say, yeah, I see a power factor change on all 3 phases. So they're actually monitoring the station when that bank closed. And if they see a power factor change on all 3 phases, that means all 3 phases closed in. So that's kind of like double confirmation. That's not added as a step, but that is added as information for you guys. Changed. All right. Okay, so confirm vacuum bottles closed, red flag, handle up. Now, we don't know at this time, because it's automated or it's supposed to be automated, if the bank was supposed to be closed or not. Now, Ryan, what do we do?
Send open signals to the vacuum bottle.
We got it closed. It's working. Everything's copacetic. We're done with our work.
Oh,
We don't know
cancel
if it
the
needs
CWP.
Cancel your CWP. Right. We don't know if it needs to stay that way. Let's let the system take control back. So you cancel your capacitor work permit. And you let automation go back to work. It might, while you're standing there, it might, after you cancel your work permit, it might just reopen back up. That's cool. That's all right. The system's doing what it's intended to do. Okay, so those are the steps to put it back into service. All right. Any questions there about takeout and restore? All right. How can you tell if a vacuum bottle is open or closed? Green flag. Let's see. Or the handle is down. Yep, we got that right. All right, so let's go back, do a share right here. Stop share.
When you're putting it back into service, would you ever have a situation where you would be on the pole closing the handle?
No,
Okay.
no, not on the pole. In fact, I know Professor, it's kind of company rules here. Professor V said whenever they closed a fuse, they use an extension stick. We don't. Okay. But whenever we close a capacitor bank, we do use an extension stick. Our company.
Mhm.
Okay. And the extension stick, the control, I'll try to find you one in the picture. The handle that goes up and down the side has got a hole in it.
Okay.
Take it in, pull it down. push it back up for closed. It's made for a stick installation. So we will do that from the ground.
Hey, I got a question.
Okay,
This
Okay.
is important. So you know how they use the SCADA to monitor the substations and the capacitors we were just looking at on that thing? Can
They
they
don't-
also do they also have a radio signal to monitor the power lines and things, or do you have to check those manually?
If you want to get readings at a specific location, you have to do that manually. If you want to get the reading for the entire circuit, that is done at the voltage regulator at the substation.
Okay.
Good question. Good
yeah,
question.
we went out and actually, and I worked on this project a little bit before I retired. We went out and installed medium voltage sensors at specific places on feeders where they could monitor, you know, the voltages and whatnot, if it was high or low, or if, you know, if they needed to kick on a cap bank or raise a regulator or lower it, whatever. But yeah, we had some of that stuff.
Yeah.
Because
It-
it seems like most of this stuff we could check from a computer or something. Like it's all
Right.
documented in one.
Yeah, some of your companies are going, I could tell you, part of this is it costs a lot.
Yeah.
I don't know if you, do I have the share screen up?
Yes.
All right, it's called Smart Grid.
Yep.
Okay, and you're gonna have monitoring devices along the entire circuit. And they use, and this is vitally important, smart metering. So the meter at your house is actually gonna send either a telephone, cellular signal, or a Wi-Fi signal that will say at the end user, my voltage, amperage, and wattage is this amount. Right,
This
when
is-
you start using smart grids and smart technology, pretty much everything that you have operating in your system has to be SCADA controlled. We'll get into that. Let me finish up capacitors. We'll get into this a little bit more. If you want to get on the engineering and smart side of this, it's very technological. But a lot of your companies, we tested it for a while. A lot of your companies are going to this. It is a huge, huge money savings for the utility. All right, so let me get back to where we were before. All right, so I've got my 3 capacitor cells right here. Now the question, and this is during transport or storage, do I need to short these cells? What I mean short is, do I need to put a wire between the 2 terminals of these when I've got these in storage or transport? True or false?
Storage? or
Yeah,
trans-
storage or transport.
Yeah.
Yeah, why is that?
It wouldn't hurt. I mean, hmm.
Surprisingly,
Oh,
even
I
with-
got the answer for that question. All right. So capacitor battery.
Yeah, don't go too far with the battery business. It doesn't
All right.
store. It doesn't store for a long amount of time,
Got
right?
it.
But it can charge.
Is that so it doesn't discharge?
Right, right. You're actually shorting the terminal so it's not able to charge. It is surprisingly under certain types of lighting, fluorescent lighting,
Mm-hmm.
these will charge. All right, in wind, when you have wind go across these things, they will charge the capacitor up to a lethal amount of voltage.
So it's collecting electrons from the air or something like that?
Electrostatic. It's a collector like a helicopter blade in the air.
Yeah.
Airplane, right? It's collecting an electrostatic charge and needs to be
That's cool.
grounded all the time.
Got it.
That's its purpose, is electrostatic storage, right? And then disbursement every 60 cycles, every cycle per second. That's its purpose, but it can pick that up from lighting and storage and movement through the air. So the terminals must be shorted at all times. Now, we got manufacturers, we were telling them, hey, when you ship us your capacitors, short them for us. And usually that's how they come. But if you get a set of capacitors comes off a truck and they're not shorted, what do you need to do?
You short them.
Short them with what?
Insulated conductor. I mean, what a
What are you
conductor,
gonna wear for protective?
a rubber glove.
Yeah, put your rubber gloves on, use all your safety gear. What we would do is we take a shotgun stick with a piece of copper on it,
Mhm.
about 2 feet long. Put that shotgun, hold the copper in it, and we just bump both of the terminals with our rubber gloves on. Once you've done that one time, put a wire in between them and just make it permanent until you use them.
What kind of material are the terminals made of?
Usually they're made of bronze.
Okay. I mean, it's just, it sounds pretty interesting that it can collect energy from light. It sounds like almost like a photo cell, that's why I was like, man, maybe the different.
Yeah, that's cool.
Yeah, it's just collecting electrostatic energy.
Yes, sir.
It is strange, but it does. That's all I can say. I'm
Absolutely.
gonna stop share on that one. And let's go back here. We're about to wrap this up. All right, so we talked about this picture before, and we obtained a capacitor work permit to be able to work on this pole, correct?
Yes.
All right, what else? What other kind of permit do we need once we start working in the vicinity of these power lines,
An HLWP.
Hotline work permit.
Hotline work permit, yeah. If you're gonna be working, and to me, this looks kind of tight. It's kind of hard to tell where the phases are right here. But if you're gonna be working in proximity or in location to this, I'd go ahead and get a hotline work permit also. So get your hotline work permit first, get your capacitor work permit. Here's the vital thing we talked about yesterday. Remember the steps that we took down prior to putting the capacitor back in service? Some people forget this. What do I need to do before I close the switches with my hotline work permit?
Cancel it.
Cancel it. A lot of people forget that. I've got a hotline work permit. They get in their minds, well, I'm not going to give up that hotline work permit until I'm finished with all of my work. All right. As soon as I put power or voltage back to this bank, I know the vacuum switches are open. Got a green flag. Before I put anything back to it, go ahead and cancel that hotline work permit, close your switches. All right, go through the whole process of putting your bank back in service. So just in case you do have a failure, the breaker is going to be automated. Okay, you're not going to have everybody's power out in that process, and then give up your hotline work permit. A lot of people forget that one step.
So when do you cancel it now?
When do I cancel the hotline work permit?
Yes, sir.
All right, it's going to go in the process right here. Me, Professor V.
Yep,
No, I'm calling on you a lot today.
that's
Do you
good.
put your high side risers on manually by rubber glove or by stick only?
Stick,
Stick only?
yes, sir.
Okay, we got into that process too. So you're gonna have a man in a bucket here. You're gonna take your shotgun stick and you're gonna put your high side riser on the primary that's up above him right there. Right, you're still gonna be really in close proximity to these phases. I would maintain my hotline work permit. Got all 3 risers on. All
Right,
right, now that I've completed that, I can back away. I'm away from my feeder primary. I'm going to use a regular switch stick. That's when I'm going to cancel my hotline work permit and close the switches with my switch stick. Cancel, then close switches.
So
Because
would that be on the putting the on the steps for the putting the back into service for the?
No, I'm not asking for you right there. Okay. I'm asking, the only question I have related to the hotline work permit is, do you need to obtain one to work in the vicinity of these wires?
Oh, I see what you're saying.
Okay. All right. So, yeah.
Hey,
that's
Mr.
the ca- Yeah, hey, mister.
Mr. Mayor, I got a question.
Huh?
You said one of the questions on there was how to tell if the vacuum bottle is closed. How did you say? Red flag and handle is up, right?
Correct. Red flag handle up, closed. green flag.
Yes, sir. Okay.
Handle down, open, right?
All right, thank you.
You're welcome. Okay, so let me unshare that. And what's left? If I must go into the primary approach distance, what do I need to obtain? A hotline work permit? Good, you guys got that. I got a bonus question, and I'm not going to give the answer. Let's see if you guys can figure it out. Bonus. What tool can I use to open the fuse on a capacitor bank if I cannot confirm that the vacuum bottle has opened? Ooh. What tool do I need to use to open the fuse if I cannot confirm that the vacuum bottle has opened?
Extension stick.
Adam.
No. You guys played with it at the field for a little bit.
Shotgun?
It's got to do, and I'll give you a hint here. It's
The
got to
load
do
break
with
vacuum thing.
Ooh,
It's
we'll
what?
get-
I can't remember the name of it.
All right. It's got to do, and it's kind of, I'll go with this terminology right here. With an unconfirmed open vacuum switch, I might be breaking load. I don't know if I am or not. I can't confirm the vacuum bottle of it. So what do I bust load with?
Oh, a load.
The load,
A
load break
load
on the shotgun.
buster. There you go.
Yeah.
There you go. Shashwing.
I could see it. I just couldn't remember the name.
Yeah,
I
yeah,
remember
yeah.
how to bust the, I mean, but I couldn't remember what the load bust was.
Yeah. For
Load
you, George,
buster.
that would be bust a move. All right. Any questions on the quiz today?
Are we in person tomorrow, Mr. Shoemaker?
Yeah, well, Professor V and I were
Yeah.
just talking about that. Your
Yeah.
exam will be tomorrow here at the college.
Nice.
Look at, I hear this. Dun, dun,
You
dun. Ah!
Hold on,
Yeah.
hold on. Look at that. You mean?
Yeah, we're gonna put you in front of a computer tomorrow in a classroom. You're gonna have to actually do your exam on your own. Can you believe it?
Bam.
Can we bring
talk
our notes?
By
Yeah,
the
these
way,
are-
wait.
By the way, these are not the droids you're looking for. What'd you say, dude?
I think he was trying to ask if we could bring our notes for his Wi-Fi cut
You
out.
can bring notes to study. You can't bring notes to look at that while you're doing the exam. The final exam is all safety. There is nothing you haven't heard, nothing you haven't done.
Safety?
Safety. It is all safety. To be honest with you, common sense.
Yeah.
Oh, I got put of that. We good.
I got plenty of that. We're good.
But why can't I just take it from home?
Because we're telling you to come to the college. And you know what else you're going to do tomorrow while you're at the college?
What's up?
Drop off your bus squeeze and your flip flop.
Yep.
Boo.
Ooh, hiss, boo.
I'll get it back in August. It's okay.
Okay.
But please.
right.
You all know how many questions are on the exam tomorrow?
I do because I made it.
Oh, how many?
25.
25. What do you
All
think?
right.
And it's
See,
all
I mean-
about safety.
V, we got a
More or
pretty,
less.
we got a pretty good class here, right?
Yeah.
Do you think we need to review it? Do you think we just need, well, if we review it, then they're all going to share the answers.
Yeah.
What do you think? Yeah, but they'll never remember the answers the next day.
You're right.
So
That's true. All right, so this is 11:09. We got a little time here. Let's take a stop right. I'm not going to record it. There you go. I'm not going to record the exam.